Good morning. Let's begin. I've just collected homework 7A from you. You've got one more homework assignment for the semester. I'm sure that comes as a relief. It's due on Tuesday the 17th, so that's a week from today. On Sunday of next week, we're going to have a bonus quiz. I've already announced that previously. And then, of course, our final exam is right around the corner. We're going to have that on Sunday, May 22nd for Section 2. Any questions related to these announcements? All right. One of the things that I've told you about previously is that as water flows through a pipe, energy is lost. We've talked a lot about pipe friction, as it's called. Here is a formula that's called the Darcy-Weisbach equation. And what it does is it relates the amount of energy loss that you're going to experience in a pipe to the velocity of flow through that pipe, to its length, the diameter of the pipe, and then finally this factor that's called F. And that's a friction factor that actually turns out to be fairly challenging to calculate. And this diagram that's on the screen here is called a Moody diagram. Kind of a funny name, but it's a diagram that's a graphical solution for the F value based on flow conditions. And actually, when you get into water resources engineering, you're going to see a lot of this diagram. There are some equations that you can use as a substitute for the graphical approach. But let me just talk through this diagram so that you understand more on what it's representing. First of all, on the horizontal axis, you can see it's saying the Reynolds number. And the Reynolds number is a dimensionless representation of the flow conditions. And one way of calculating it is the velocity times the diameter divided by the kinematic viscosity of the fluid. And from that expression, remember that when the Reynolds number is greater than 4,000, that tells you have turbulent flow. When it's less than 2,000, that means you have laminar conditions, and then in between is something we call a transition range. So the simplest way of calculating the friction factor F is in those rare cases where the flow conditions are laminar, all you have to do is have 64 divided by the Reynolds number. And that's where this F value curve comes from. But it's pretty uncommon to have laminar flow conditions, and so I don't think you'll actually ever use this formula. More commonly, you're going to have a Reynolds number that is relatively high. As the water's flowing through the pipe, you can see Reynolds numbers 10 to the 5th, 10 to the 6th, even beyond. On the right vertical axis, this is called relative roughness, and since it's small you may not be able to see what it's saying, but the relative roughness is K sub S divided by D. The K sub S in this ratio is called equivalent sand roughness. And what it is it's a measurement that relates to the material type. And pipes are made out of a lot of different things. You can make pipes out of galvanized iron, it can be stainless steel, it may be cast iron, PVC plastic, HDPE plastic, drawn glass tubing. And so there's a huge range of different materials that water flows through. And each of them has a certain roughness. Now, if I was going to draw a basic sketch of a pipe, maybe it would look like this. You know, it's just two parallel lines and they're each flat. But this is an oversimplification of what the pipe actually looks like. If we're going to zoom in on a certain section of the pipe and look at how rough it is, then actually from a microscopic level, the pipe itself has a lot of variations. And each of these ridges is, if you're looking at the pipe material, maybe if this is cast iron, there's variations in the shape, and then the water that's down here in these valleys in between the ridges is going to have different experiences with the water flowing past than the top of the ridge. So if a pipe is rough, it's going to induce a lot of turbulence. So think about the water that's flowing through a pipe that's like this because the water is going past these boundaries, it's going to cause more turbulence than if the pipe itself was very smooth. If you have relatively small ridges, then that's going to cause less of a disturbance in the pipe. And so that's why we need to keep track of the ratio of the K sub S, which is the equivalent sand roughness. It's just telling you if you're going to represent these ridges in the pipe, what if it was a piece of sand? What would be the diameter of the sand, the equivalent sand roughness diameter? And then this D is talking about the diameter of the pipe itself. So you're relating how tall are those ridges to the diameter of the pipe and trying to find out the ratio between the two, because that ratio is what you're going to use on this vertical axis on the right. So you would find the intersection of the Reynolds number and then following these curves, which each correspond to a relative roughness. So let's say, for example, that you have a K sub S to D. So that's talking about the ratio of the roughness to the pipe diameter. And what you have is, for that ratio, 0.004. And you know that your Reynolds number for a certain flow condition is 5 times 10 to the 4th. Let me show you how you'd find the F value for that. So you'd start with the K sub S to D, and you'd find this curve. For part of the curve, it's flat, and then it begins to go upward. So you'd follow this black line and try and find out where does it intercept 5 times 10 to the 4th. So here, 5 times 10 to the 4th is going up, and we're going to find where does that line intersect 0.004. So it's going up, and here's the intersection with 0.004, and we go to the left and find out that the F value would be 0.031. So part of this range is labeled as rough turbulent zone. That's when it's flat. And rough turbulent zone means it doesn't matter if the Reynolds number is increasing even more, but the F value only depends on the relative roughness. And then there's a certain section where the line is more curved, and the F value, when you have the transition zone, that means the F value depends on both the Reynolds number and also the relative roughness. So calculating this F actually is a real challenge, and when I'm teaching water resources engineering, we spend about 3 class periods talking about different ways to estimate the F value. You know, this graphical approach, the Moody diagram, is just one way. There's also formulas like implicit equations where you're solving for F depending on the velocity of the flow through the pipe and so on. And so just to remind you about an example that we've seen previously, one of the problems that we solved in class was looking at water flowing through a pipe that's connecting 2 reservoirs. So let me ask you, why is water flowing from the reservoir on the left to the reservoir on the right? What's driving that flow? Yes? It's the elevation difference, exactly. So what's driving that flow is a delta Z. So how do we find out what is the flow rate between the 2 reservoirs? We could solve the energy equation. Remember, if we were going to take a look at the energy equation, we have the pressure head term, the elevation term, the velocity head term. We have in here on the left side H sub P, and then we have the pressure head term at 2, elevation for 2, the velocity head at 2, H sub T for the turbine, and then finally HL. And you may remember that HL has 2 components. The first component is H naught, which is local losses, and then there's also H sub F, which is frictional losses. And so one way of solving for H sub F is with this Darcy-Weisbach equation, which is on the screen right now. So H sub F is F L V squared divided by D2G. And so what you can do to find out what is the flow rate through the pipe is you say, let this be location 1, the upper reservoir, let the lower reservoir be location 2, and you find out how much energy is there at 1, how much energy is there at 2, and then you're solving. The only thing that's unknown is what is the velocity in the energy loss section of it. But the challenging thing is if you don't know the velocity, that means that you don't know the Reynolds number. And if you don't know the Reynolds number, then you can't calculate the F value. So there's more than one unknown, because the unknown is both F, which depends on the velocity, and V itself. So part of the challenge when you get into 341 is the fact that you have two unknowns, and so you have to do this in an iterative way. You have to make an assumption on the F value, and then do the calculations based on an assumed F value, checking the F value, and seeing if the assumption is valid. So that gives you an idea about the Moody diagram. I'd encourage you to look it over in your textbook. It's found in there. We're now going to talk about local losses, which is the other component of the losses. You know, there's the two pieces. There's the friction losses and the local losses. You'll notice here it's calling these local losses minor losses. That's just another name for it. And sometimes they're called minor losses. The reason for it is that compared to friction losses, which are usually very big magnitude, sometimes these local losses are relatively smaller. So you may lose 10 meters of head due to pipe friction compared to only 1 or 2 meters of head being lost due to things like water flowing around a bend. So here on the screen you can see something that's called the separation zone. And these are streamlines that's indicating the direction of the flow. And before the change in direction, the streamlines are parallel. It seems like the flow is very well established and sort of uniform. But then as the water goes around this corner, the flow is having to reestablish the uniformity. Like there's in the transition a lot of turbulence. And because of the turbulence, there's going to be a loss of energy in the form of decreased pressure. And so what we can do is we could connect pressure gauges upstream and downstream of this transition and measure how much energy is being lost in the form of a decrease in pressure. And experimentally, that's what they do in order to characterize something called a K value. A K value gives you an idea of whether a lot of energy is being lost or just a little bit of energy. And so the way that you would measure the K value is use a differential pressure gauge or a manometer, some way of saying upstream and downstream what was the change in pressure. So you'd physically measure that change in pressure. You'd know the velocity, the flow through the pipe, maybe by quantifying the flow rate using the volumetric method. And so both of these things can be measured, and you calculate a K value. And there are tables full of K values that previous people, engineers, have done experiments and characterized the K value so that you can use it for design. Because when you're doing design, you have to predict how much energy is going to be lost as the water moves from one place to another. You know, hydraulic design can include a pipe network where water is flowing from a desalination plant on the coast towards people's homes in the suburbs. Or sometimes the networks can be a lot more simple than that. Sometimes the flow is the flow of crude oil through a pipeline. And you have to be able to predict what is the pressure, because if you don't have in enough pumps, then the flow rate won't be high enough to achieve the capacities that you need to see. So here's an example of a table that's taken from your textbook, and it shows lots of different K values depending on a range of conditions. Let's look at this bottom table first. These are called threaded pipe fittings. And a pipe fitting is a way of turning off the flow. So maybe you've noticed at the sink in your house, there's a way underneath the sink you can turn a valve and it will switch off the flow to the sink itself. You know, a lot of the plumbing fixtures in the house have the same thing, where if the sprayer is malfunctioning or the faucet on your kitchen sink, you can turn it off underneath by using a valve. but there's different kinds of valves, and some valves take a lot more energy out of the system as water is flowing through it. Let me just do a very small illustration to show you a couple of different valves. So if you have a pipe, and above the pipe is a gate, it's just a piece of metal, and then there's a slot in the pipe. When the gate is open, the water flows through it with no disturbances. But then this gate can just drop in and completely stop the flow. And of course, if there's no flow, there's not energy losses. But the point is that the gate can move completely out of the way, and it doesn't disturb the flow at all, so there's very little energy loss. So here you can see it says gate valve, wide open, and the K value is 0.2. That's a very small K value. It means that very little energy is going to be lost for a gate valve. But another kind of valve is called a globe valve. A globe valve, you can think of that as a ball that's inside of the pipe. And the ball that's inside of the pipe has a small hole in it. And the hole rotates because here is a handle. And you can turn the hole so that if you want the flow to go through the pipe, then now the hole is facing the flow. And so all of the water that's going through this pipe has to go through a small, tiny little hole. And so you're going to have a high K value for that. Here for the globe valve, when it's open, you have a K of 10, because that means you have actually a smaller diameter pipe inside of the pipe. And then when you want to close the gate valve, the globe valve, you turn it, and so that the hole isn't intercepting the flow, and then the water can't pass through at all. And so you have to know in a system, whether it's a house or inside of the streets where the water is flowing underneath the roads, you have to know what is there. There may be a T, or the water is going around a curve in an elbow. And so think about the case of what if you have water going on a curve. So a pipe suddenly changes direction. There's going to be a lot of turbulence when the pipe suddenly changes direction compared to if it was more gradual. And so if the water is changing direction gradually, it's causing less turbulence inside of the pipe section, and the K value will be lower. So here in these smooth bends, a 90-degree smooth bend, the way that they are explaining what K value you should use is the ratio of the radius to the diameter. And the R that they're talking about is the radius of curvature. The drawing is a bit small, so let me show you what that means. If you have water that's changing direction like this, here we have, to begin with, is a certain pipe diameter. Let's say here the diameter of the pipe is 1 centimeter. And then the radius of curvature is, if you draw a curve through the center of the pipe, the radius, let's say as an example, is 4 centimeters to here. So that's saying whether the curve is sharp or gradual. So for here, the R to D would be 4 to 1. And so you'd find for the R to D of 4, then the K value is 0.16. But you can see if the R to D is 1, the K value is higher. So an R to D of 1 would be, what if you have that same 1 centimeter diameter pipe, but now suddenly it's changing very quickly. So here your radius of curvature is 1 centimeter. If the pipe direction, if the flow is changing suddenly, there's going to be a lot more turbulence and energy loss, and so that's why we now have a higher K value, a K of 0.35 for a sudden change in direction. So all of these different K values are talking about whether it's a gradual or a sudden transition in pipe diameter, in direction, and it's a way of estimating in advance how much energy is going to be lost because of these local instances of the flow being disturbed. So just to summarize, there's two ways that energy is lost. One is through pipe friction, which we've talked a lot about that. We've talked about how the pipe is applying a shear stress to the flow as the flow goes past the material of the pipe. But now here in the local losses, we're talking about these very specific disturbances to the flow, the turbulence that it causes, and then the resulting change in pressure. Are there any questions about this slide or just about local losses in general? Here's a specific local loss. This is showing the case of what if the flow diameter is increasing. So on the left, before the transition, the conditions were uniform. A relatively smooth flow. You can see from the streamlines that everything is parallel and well established. But then when the pipe diameter gets bigger, there's a zone of separation. And anytime you have a big zone of separation where there's turbulence and countercurrent flows, that causes a decrease in the amount of energy that's available for the flow. And one way of estimating how much head loss there is in a case like this is to look at the velocity before the transition compared to after, taking the difference of the two, squaring it, and divided by 2g. So that's just one way of estimating the energy loss at a transition. Now the extreme is what if the diameter of the pipe downstream is very, very large. So here is on the board is a drawing of pipe that's flowing into a reservoir. Think about the water inside the pipe before it gets to the reservoir compared to just after the water is inside the reservoir and how things are different with the energy. Inside the pipe, some of the energy exists as velocity head. And you remember that there's three places the energy can be. The energy can be tied up as pressure, elevation, and velocity. So between here and here, these 2 points are very, very close together. The elevation difference isn't changing, and the pressure isn't going to be changing very much, but the big difference is that when the water is inside the pipe, there's velocity head, but as soon as the water gets into the tank, the water inside of the tank has no velocity, and so suddenly you lose all of the velocity head. And we're going to look at a graphical representation of that in just a moment. So here, this is saying the head loss is equal to the velocity head. You're losing all of the velocity head when water enters a tank. That's something you need to make sure to show when we're doing these drawings of energy in systems. We're going to spend the rest of the class period looking at graphical ways of representing how much energy is in a system. And this is actually something that's very common to do for design drawings if you're designing a chemical plant or designing a water treatment plant. It's pretty common in the drawings of the system to have sketches of where is the hydraulic grade line and energy grade line, just so that the people who are building the plant can have an idea what is the pressure going to be at every location in the plant, and if there's enough energy for the water to flow by gravity from one point to the other. So in this drawing is a tank connected to a pipe, and the water is flowing from the tank through the pipe and it's exiting as a jet. So the water comes out as a jet. And you'll notice that there's two things on here, the EGL, which stands for energy grade line, and the HGL, which stands for the hydraulic grade line. Inside of the tank, the EGL and the HGL are at the same location. The EGL is all three terms of the energy equation. EGL includes the pressure head, elevation head, and velocity head, all three together. That's the EGL. But the HGL, the hydraulic grade line, only includes the pressure head and the elevation head. The HGL doesn't include the amount of energy that exists as the velocity head. And that's why, if you look at this drawing, there is a gap between the two lines. And how far apart these two lines are depends on the velocity of the flow. So here this is showing v squared divided by 2g. These two lines are relatively far apart because the water is moving quickly through the pipe. The physical interpretation of where these lines are drawn to, in the case of the HGL, if you have a piezometer in the pipe, if you puncture the pipe and then you have a tube connected to that pipe, the water level is going to keep rising and rising, and then finally it stops depending on how much pressure is inside of the pipe. And it stops at the location that we call the HGL. So here is a piezometer, the tube on the left where the water is going up, and then it stops at the HGL. Let me ask you this. Why is the water level higher for this tube compared to the piezometer? So the tube on the right, you'll notice that the water level rises a little bit higher to the EGL. What do you think? Because of the velocity. The velocity is being transferred into additional pressure inside of that tube, because you'll notice it's a different kind of an opening. The opening on the left isn't intercepting any of the velocity, but the opening on the right is actually facing into the flow, and so the water in the pipe is moving along. It has some velocity head, but suddenly it comes to this stagnation tube. It's an opening inside of the pipe where it's intercepting the streamline of the velocity, and so all of the energy that's tied up as velocity is exchanged into a little bit of additional pressure, and that pushes the water up just a little bit higher. And so that's the physical interpretation of the energy grade line, is how high the water will go to based on the elevation, pressure, and then also taking the energy that exists as velocity and converting that into some additional head inside of the tube. All right. Why are the lines going down? Why aren't the EGL and the HGL flat? What does it mean that these lines are sloping downward? Friction. It means that energy is being lost because you're losing, the EGL line is getting lower. Then that means that you've lost energy because of pipe friction. And these two lines are parallel because when you lose energy due to pipe friction, what you're losing is pressure. And pressure is in both the HGL and the EGL. Pressure, so if you lose 1 meter of pressure head, then you're going to lose that 1 meter of pressure head from both the EGL and the HGL. So these drawings show actually a lot of information. Why is the EGL line above the water when the jet goes out? That's because as the jet is moving outside of the pipe, it still has velocity. And so the velocity head is greater than the amount of energy in the flow is more than just how high the flow is above our datum, the vertical datum. It also has some kinetic energy as well. There's one last thing I want to mention about, and that is where the two lines are together inside of the tank, and then they separate. There's a little bit of a line here where it's extra steep. And what that part of it means, it's just trying to show that when you have the water here before the opening of the pipe compared to inside the pipe, there's some difference because the energy that is in the water here, you have some elevation and then you have some pressure. But then the water that's inside of the pipe, you still have elevation above the datum and there's still some pressure, but also now you also have velocity head. And so there is a decrease in pressure as the energy goes from pressure into having some of the energy being as the velocity head. And so there's an exchange. And that's why suddenly you'll notice the HGL is getting lower than the EGL because you're losing some pressure so that there can be velocity head inside of the pipe. Any questions from this drawing before we move on to the next sketch? Here is one that's showing a pump, and it's showing that the energy suddenly goes up because of a pump. And so the two lines are separated. EGL is always on top of the HGL. Most likely you'll have drawings like this in the homework and then maybe even on the final exam. So you have to be able to show each of the important characteristics for the system that's shown on the problem that you're working. And here you can notice that The lines are going downhill, downward because of the energy loss due to pipe friction, but then the main characteristic is a sudden increase in pressure due to a pump. That's what a pump does, is it has a sudden boost, and then after the pump, then the line is sloping downward again because you still have energy losses even after a pump. In a lot of ways, a pump and a turbine are opposites. A pump adds energy in the form of pressure. A turbine extracts energy in the form of reduced pressure. So here the water is flowing from an upper reservoir to a lower reservoir. And so you'll notice the EGL and the HGL are sloping downward because of pipe friction. But then suddenly here's the turbine and you're losing a lot of head because the pressure is decreasing a lot due to that turbine. And then there's kind of a strange thing here. The diameter of the flow section is increasing. I guess they're doing that so that the velocity can be lower when the water gets into this tank. They don't want it to be a huge jet of water going into the lower tank. So they're smoothing out the flow. And as they do that, the EGL and the HGL get closer together because the velocity head is decreasing. So that's one small element. The main thing to take away from this sketch is that you have a sudden decrease in head due to the turbine. In the case of a nozzle, think about what a nozzle like this is doing to the flow velocity. If you have the diameter wide and that the diameter is decreasing, that means the velocity is going up. And so you're going to have more of the energy inside of the flow as velocity compared to as pressure. And so here the EGL and the HGL are relatively close together before the transition, but then after the transition they're further apart because remember the distance between the EGL and the HGL, that gap is the velocity head. And if you have more velocity head, then the distance between the EGL and the HGL is going to be greater. And then once the water jets outside of the orifice, the HGL is on the water surface itself, but the EGL is above the water surface because there's still some velocity head in the flow as the water is spraying out of the orifice. Okay, here's another one. If we have a diameter change, if the pipe is big diameter and it's going to small diameter, you notice that the EGL and the HGL are close together here, but then they're farther apart when the diameter changes. That's because you have a faster velocity here. And so if you have a faster velocity, then the velocity head should be bigger. Why is the slope steep for the small diameter pipe compared to the large diameter pipe? What does that mean, like how steep the slope is? Exactly, right. So remember that the energy loss due to pipe friction, if we look at the Darcy-Weisbach equation again, we have H sub F is F L V squared divided by D 2G. Here in this pipe, the diameter is small so that you'll have a high velocity. The flow velocity is high. That means you're going to lose more energy due to pipe friction. So a steep slope, this section of the pipe has a steep slope because you're losing energy very, very fast because the water velocity is high. So it's important to be able to show all of these things on a sketch. And I have a handout I'm going to give you in a moment so you can practice doing the EGL and the HGL. So you should always, first of all, always label both of them. And in every case, the EGL will be above the HGL. Sometimes it takes a little bit of practice, though. You should do these sketches using a pencil, not a pen, because you maybe are going to need to erase the line. And one of the things I want to point out here is that the HGL intercepts the water surface, but the EGL is above the water surface, and then suddenly it goes down again. So here is the velocity head is being lost. As the water goes in see these little blue lines inside of the tank? These little blue lines are kind of just trying to give you the idea in your mind that all of the energy that exists as the velocity head is lost because the flow just diffuses. When the water goes into that tank, all of the energy that existed as velocity head is just poof, it's gone. And so this is the graphical representation that the EGL is above the water surface and now it's at the water surface itself. So are there any questions about this sketch? Things that you don't understand from the drawing perspective? Okay, there's a point being made here. That is, the EGL and the HGL are not affected by where the pipe is. The only thing that affects the slope of this line is the rate that energy is being lost. But think about where the energy is. There's three places. I've told you before that the energy can exist as pressure, elevation, and velocity. So when water inside of a pipe is going uphill, this is a pressurized pipe, and so the water is flowing uphill because the pipe itself is increasing in elevation. You're gaining Z, but you're losing pressure when the pipe gets higher. But the EGL and the HGL, it doesn't matter because both elevation and pressure are in the HGL. So although the physical elevation of the water is increasing and you're gaining Z, you're losing pressure head at the same rate. And so here you can see that the HGL is steady. It doesn't matter if the pipe is going high or if it's wiggling back and forth. The decrease in pressure is constant, and it's a function of the friction in the pipe. And the same thing is true of the energy grade line, that there's a consistent decrease due to the pipe friction, but it may be that inside of the pipe the pressure is positive, and then because of the height getting higher and higher, you may have a negative gauge pressure. But even if you have a negative gauge pressure, you're still losing energy inside of the pipe due to the friction losses. And then the thing to see at the exit of this pipe is that you always should have the HGL terminate at the open surface of the water. And then here, since it's a jet that still has velocity head after the water exits the pipe, then the EGL is above the water surface after it exits the orifice. All right, so here are a couple of the key characteristics. Now, you may see problems like this on the homework or even on the final exam, and you have to do the sketch not necessarily to scale. I'm not looking for you to do a perfect scale drawing of the EGL and the HGL, but you should have certain elements in your drawing that illustrates that you understand what's happening to the energy in the system. And so here I've highlighted with the red arrows a couple of important things that you need to show when you do sketches of your own. The first one, the arrow is pointing to the divergence of the EGL and the HGL, because the water is stationary inside the tank, but as soon as it's inside the pipe, now the water is moving. That's the first thing. The next characteristic that you should illustrate here is that the EGL is above the HGL, and the distance between them is a function of the velocity head. And then finally, this red arrow is just illustrating that the water, as it exits the orifice, still has some energy because of the velocity head, and so the EGL is above the water surface. And then remember, here at a pump, it's a sudden elevation increase going up. And then there's still losses after that. It's not that a pump prevents there from being any energy losses. It's just both the grade line and the energy grade line and the hydraulic grade line go up and then are gradually decreasing from there. Okay, so I have a handout for you, and what we're going to do is take a few moments for you to collaborate with your colleagues and try and do the sketches on this paper. I'd encourage you to use pencil if you've got one, because you may need to take an iterative approach. You can't always just draw it right the first time, because remember, what you want to have is you want to have the EGL and the HGL starting at the water surface and ending at the water surface. And the lines, how steep the slope is a representation of how much energy loss you're experiencing. So it's fine to talk and try and figure this out together. Your drawing may look a little bit different from this, but there are some things that you have to have. So let's talk about what has to be present to be correct. This one has to be not as steep as the first pipe. The first pipe is more steep because the diameter is smaller. So you're losing energy more quickly through the small diameter pipe. Okay, so that's one thing, is that here you have steep, here you don't have steep. These two lines are further apart, so the gap between the EGL and the HGL is further apart. A big gap means that you have more velocity head. So that makes sense. Here is a small pipe, here is a big pipe. In the big pipe, you have less velocity head. Yes?
The part looks like if there is a turbine or something, that's how it goes down. I don't get why.
Oh, this?
Yeah.
It's because here we have a local loss. The transition, the water is going from a small diameter to a large diameter pipe. So we talked earlier in the class about K values. And so this drop, you're right, a turbine does the same thing, but this case is a loss of energy that's sudden because of the transition in the pipe diameter. And then one more thing that's a must is the EGL and the HGL have to start at the water surface on the left, and on the right, the HGL should be at the water surface, but the EGL should be above it. So it's tricky to draw these so that it starts and ends where you want it to be. It's easy to have the flow going and then accidentally maybe you're too low or accidentally you're too high. So you have to do it in a pencil and sort of try it over and over again until you get it to match up the way that you need to. Are there other questions about the first one? Here's the other one. How do we know that this is a pump instead of a turbine? Yeah, the water is flowing up. So here is a tank that's low. Here is a tank that's elevated on the right. And the arrow says the water is flowing from the lower tank to the higher tank. So the only way that can happen is if this device is a pump. It wouldn't work if it was a turbine. So you have the water flowing. That means you're having a decrease in the pressure. This line is thick. That means it's a bigger pipe. Question?
Yeah. My EGL and HGL, do they have to touch the pump?
No, they don't. So the question was, does the line have to touch the pump? And no, it doesn't. In this case, it just did because I started drawing the lines a certain slope, and that's where it ended up. The only thing that you have to have is you have to have a big jump up because of the pump. You have to have that the lines are closer together here because this is a larger diameter pipe. It should be less steep. And then it terminates at the water surface for the HGL. All right, we're running low on time. Let's just remind ourselves once more that you have a quiz coming up on Sunday, the assignment on Tuesday, and then after that, the final exam. So, have a great day. I'll see you next time. Thanks, you too.